So today what we want to start talking about for our new unit is the exponential function. So we're going to start talking about exponentials. And as you can probably guess from the title, exponential, we're going to be dealing with exponents, which is pretty cool because we spent a lot of time, earlier, a couple of units going over the laws of exponents and how to deal with exponents. So we're going to be talking about exponential functions. Today specifically we want to be dealing with exponential growth. Tomorrow we'll deal with exponential decay. But an exponential function is when the variable, instead of being what has the exponent, instead of being the base, for an exponential function, the variable is the exponent. So now we're talking about, instead of having, x having an exponent, x squared means x times x, right? It's that repeated multiplication. And so x is the base. It's what's being repeated over and over and over again. Now we want to talk about x actually being up in the exponent. So 2 is the base. It is what is being repeated in the multiplication. The problem is we just don't know how often it's being repeated. We don't know what that exponent is. That's the question. How many times am I multiplying 2? And so this is what we mean by an exponential function. The variable is up in the exponent. We do end up with some very interesting graphs and things because of it. This is what we call the generic form of the exponential function. So CA to the x power. And this is just a basic, plain, lovely exponential function. When we look at the exponential function, there are parts to it, so we do want to remember a couple of things. This is our constant, or our coefficient. It is a number. It is a multiplier. It's being multiplied times this. A is the base. Vocabulary. And then this is our exponent. So just to remember, so A is being taken to the x power. And then it's being multiplied by c. Because remember, order of operations. You have to do exponents before you can multiply. So you'll never be able to multiply A and C. Because A is being taken to the x power. You've got to do that first. Then you can multiply it times the constant. When we call it exponential growth, the key factor for something being exponential growth is that the base, A, has to be greater than 1. All right? So if that base, the A, is greater than 1, then we know that we are dealing with exponential growth. And as you can probably figure out, if it's less than 1, then we're dealing with decay. But this is the idea, exponential growth, A is bigger than 1. Things that we want to know about exponential growth is, what does that look like on a graph? So things that you want to know about exponential growth are the parts of the exponential graph. So one thing to know is that the exponential graph has what we call an asymptote. An asymptote is an imaginary line, it's a dashed line, that a graph gets closer and closer and closer and closer and closer and closer to, but it never quite touches. It's like a brick wall. You can drive pretty close to a brick wall, but you really don't want to drive into the brick wall. You get closer and closer and closer to it, but you cannot actually touch it. And so it's a boundary. Exponential functions have a limit. They have a boundary. And so that asymptote is a horizontal line, and in general, it's just right there at 0. So you have a horizontal line at 0, and that is your asymptote. So all exponential functions have an asymptote. So that's our asymptote, and that's the limit. So our graph is getting closer and closer and closer to this, but never quite touching it. Another important part to your exponential graph is the pivot point. It's its turning point. And so our turning point starts right here, usually on the y-axis, all right? And it is above the asymptote. And this is the point where the exponential starts acting differently. It's a turning point for it. For exponential growth, growth is getting bigger. It's going up. So on the right-hand side of the turning point, in fact, it's going as far away from the asymptote as it can get, as fast as it can get. But on the left-hand side of the pivot point, of the turning point, is where it's getting closer to the graph. So on this side of the pivot point, it's getting as close to that asymptote. It kind of flattens out almost, like it's getting close to that asymptote, but it never quite passes the asymptote. And then on this side, it's just shooting up as quick as it can and going up, 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 and away. And so this is what the exponential growth graph looks like. Again, I'll usually refer to this point, its turning point or critical point. I usually call it a pivot point. And then the curve itself, you know, that's the actual graph. Like we had a parabola for the quadratic. That was its shape. The exponential growth is this curve. So it flattens out on one side, and then it gets really big, really quick on the other. And so these are the three parts of the exponential graph that we're always going to be looking for: the asymptote, the pivot point, and the curve. So the question is, where do we find those pieces of information in the graph? So let's look at the equation again. And I'm going to add just one thing to the equation out here. I'm going to add a plus k. Okay. This, and then we'll talk some more about this as the week goes on, but all that we need for our graph is here in this equation. Things that you need to know is whatever the number is out here, this is where your asymptote is. A lot of times there's not a number out there. That's why it usually ends up being at 0. But if it's plus 2, then we put our asymptote at 2. If it's minus 4, we put it down here at minus 4. And that is the first thing that you want to locate when you are graphing, because you can't draw your graph if you don't know where its boundary is. We don't know where it's getting closer to. So we have to know where its boundary is. That's what you're going to do first. The second thing we need to know is where's our pivot point. And so that's what C is going to tell me. C tells me how many spaces above the asymptote is my pivot point. If C is equal to 1, then it's just 1 above the asymptote. If C is 5, then it's going to be 5 spaces above the asymptote. And then if it's exponential growth, we know our curve is going up. And so A, the base, is always going to tell us whether we are dealing with growth or decay. And tomorrow we'll do some graphing with decay, but today we're just going to be focused on growth. So really we need to know our asymptote and our pivot point, and then we can draw our curve. Let's look at a couple of examples. So if I've got my graph, and I know that I have all right, so we are going to graph an exponential. So let's look at a couple of different examples that we can do here. So if I have the equation y equals 3 times 2 to the x power minus 1. All right, and I actually want to graph this. The first thing I need to realize is that x is in the exponent, so it's an exponential. That's how I know what its shape is going to be. The next thing I need to figure out is where is my asymptote? And this number out here on the outside always gives me the asymptote. So this tells me that my asymptote is at -1. So I need to draw a dashed line, not a solid line, because solid lines imply that it's part of the graph. This is not actually part of the graph, it's the boundary for the graph. It's what the graph can't pass. So this is my asymptote. I got my little dashed line right here at -1. This is what I'm going to, that's my boundary for my graph. Next thing I need to figure out is where is my pivot point? So this is going to tell me where is my pivot point. My pivot point is 3 spaces up above the asymptote. Don't start at the origin. Start at the asymptote. And I'm going to go up 1, 2, 3. That's my pivot point. So found my boundary first, figured out how far from my boundary is the pivot point, and then this number is bigger than 1, so that's telling me that it is growth. So that means that it is going up to the right. This is getting bigger. It's growth. It's going up. So I know that on this side, this needs to be getting closer and flattening out down here. I can't go past the asymptote, but it's getting closer. And then on this side, it's just going up. Growth. So the 3 parts to my graph: asymptote, pivot point, and then if it's growth, it's going up. And that is what the graph looks like. Well, what are the types of things that we use this kind of a function for? We're going to be doing our project this time. We're doing interest. Interest is something that is exponential. Exponential growth and decay, we're generally dealing with things that grow by percentages. And so when we think about that generic formula, this is the exponential growth model, all right? Things that grow by percentages or grow exponentially, there's usually three pieces of information that are involved. We have some kind of starting value. What is it worth at the beginning? We have some kind of time period, time frame. Is it growing every year? Is it growing every hour? Is it growing every second? What is our time frame? And then we have whatever our percentage that we are growing. I'm growing 5% per year, or 8% per year, or it's 25% per year. A is our growth factor, or tomorrow we'll talk about it being our decay factor. Now, it is interesting to point out that your growth factor is not just the percentage. The growth factor is 1 plus your percentage that's been changed into a decimal. Remember, we never put percentages in just as percentage. If something is 25%, then I'm going to have to change that to a decimal, and it's going to be 0.25. Remember, you just divide it by 100. If it is 3%, then that would be 0.03. If it's 2.7%, then that would change to 0.027. You're going to divide it by 100 and change the percentage to a decimal. But the growth factor is always going to be 1 plus that percentage. So this is usually a number like 1.25, 1.03, 1.027, and that is your growth factor. So if we look at a problem, for example, that says that we bought a car, bought a classic car. So somebody has restored this classic car, and we bought it for $10,000. But we find that it is gaining value, and that's not usual for a car. Usually cars are losing value, but if you buy like a restored car, classic car, an antique car, something as an investment, and you're planning on taking care of it, because they are rare, they can gain value. Bought a classic car for $10,000, and it's gaining value at 3% per year. And then the question will be, what is it worth in 10 years? So we can use our exponential model to figure that out. Remember, it's CA to the X. So C is our starting value. What was it worth at the beginning? Well, in this problem, it was worth $10,000 in the beginning. So 10,000 is my beginning number. Then I need to know, what is my time frame? Well, the time frame that we're looking at is 10 years. We said that the exponent, the X, was our time frame. This was our time, and we're dealing with years, and this was my start. And then we have to find our growth factor. A is our growth factor, and remember we said that that's going to be 1 plus the percentage as a decimal. Don't forget, don't do 1 plus 3. That's going to give us a very bad answer. First, I need to change my percentage to a decimal. So if it is 3%, that is going to be 0.03. And then I have to add that to 1. So this is going to be 1.03. So then I can go to my calculator, and when I'm in my calculator, I can just type in the numbers that I have in my formula. Remember, it's just a formula, and so it works just like a formula. We just want to type in the numbers there so that we can look at that on our calculator. So I'm going to have to type in 10,000. So that's 4 zeros. Yep. All right. 10,000. And then I have 1.03. And then I'm going to take it. Now, if you've forgotten how to do exponent, it's the little caret top. So I'm going to take it to the 10th power. So 10,000 times 1.03 to the 10th power. And that is going to give me $13,439. $13,439 and it looks like if we round, now this is money. Money is 2 decimal places, so that'll be in 16 cents. So this is going to be the value of that car after 10 years. Starting value, time frame, and then 1 plus the percentage. And that's how we use the exponential growth model.